As you can see, we're going to discuss series in this lecture, and we have to differentiate between the idea of a sequence and a series. Remember, a sequence is nothing more than an ordered collection of values. So a sequence would be a set of a first element, a second element, a third element, a fourth element, and most likely an infinite number of these entries. And they're in a particular order. So that's what a sequence is. A series, the idea behind a series is we take that sequence and we add up each of the pieces. So we will write it something like this. We would say the sum from, and the end, this is called an index, the index n equal 1 to infinity, okay, of a sub n. And that means we're taking that sequence above, we're taking the first entry, and then adding the second entry, and then adding the third entry, and then adding the fourth entry, and we keep this addition up infinitely. Okay, so a sequence is a list, a series is a sum of a list, a summation of a list. Now, there's nothing particularly magical about the index we use. See, I call these a sub n's, and so I'm letting n change from 1 and incrementing by 1 each time. So n starts at 1, and then it increments to 2, and that's called the index. N is called the index. We could have used a different index name, letter, a different index name. We could have said the sum from k equal 1 to infinity of a sub k. And so when k is 1, we have a sub 1. And then we add and we change k to 2. When we change k to 2, we have a sub 2. And then we add and change k to 3. And so it's this, again, the name of the index is not important. It's the idea of what's going on behind the scenes. And so you'll have to get used to, most of the time I use an index of n. And sometimes books use an index of k, some use an index of j, some use an index of n. And you'll just have to adapt specifically to what a particular homework problem or your reading material says. Now, from this, we define what are called partial sums. And so what we see here is an infinite series, an infinite sum. And we want to talk about partial sums, so we're not adding infinitely. So partial sums are generally indicated with a capital S. For instance, capital S subscript 1 means add the first entry. So it would just be a sub 1. That's all there is to it. Capital S subscript 2 is called the second partial sum. And that 2 means add the first 2 entries. So it would be a sub 1 plus a sub 2. And then, of course, S sub 3 would mean add the first 3 entries, a sub 1 plus a sub 2 plus a sub 3. So if we continue this, of course, S sub n would mean add the first n entries. So it would be a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, and we would continue this until we get to a sub n. If n was 1,000, we'd be adding up the first 1,000 terms. Now, from this set of partial sums, we can create a sequence. That is this. If the sequence, let me write this down, I'll be right back. So as I was saying, it's a sequence of partial sums. See, we can create a sequence of partial sums, and each partial sum is adding so many terms together. So we can create a sequence out of all those partial sums. If that sequence converges to a number s, see if it converges to a number s, which means if we take the limit of the s sub n's as n goes to infinity, we get the number s. Then the series that makes up the infinite series, that is the sum of the a sub n's from n equal 1 to infinity, we say that that converges. And the limit s is called the sum of the series, okay? So let me write that this way. So if the limit of the partial sums exists and is finite, is some number n, then the limit s is called the sum of the series. And of course, the way we would write that is the sum, this infinite sum from n equal 1 to infinity of these a sub n's, we would say is equal to s. If we add infinitely, we get this number s, which is the limit of the partial sums. Or another way we could say that is a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 and forever. If we add forever, we get the number s, that the series has a finite sum. Now, on the other hand, this is what we say when it converges, is when that limit exists. If, instead, the limit, as n approaches infinity of the partial sums is plus or minus infinity or does not exist, then the series sum from n equal 1 to infinity of the a sub n's diverges. That's what we say, is it diverges. Okay. So if the limit exists, it converges. If the limit doesn't exist or is infinite, it diverges. Let's look at an example. An example will go a long way. So let's consider the series, which is the sum from n equal 1 to infinity of 1 over 2 to the n. Now, so let's stop and think what this looks like. When we let n be 1, we have 1 over 2 to the first, or just 1/2. And then we add and we change n to 2. So when n is 2, we have 1 over 2 to the second, which is 1/4. And then we change n to 3 and add, and when n is 3, we have 1 over 2 to the 2 to the third, which is 1/8. And if we continue doing this, then when n is 4, we'll have plus 1 over 16. And of course, this continues infinitely. Okay. Now, the question is, does this series converge or diverge? That is, does this series add to a finite number? So let's consider the sum of the partial sums, a list of partial sums. So the first partial sum says we're just adding the first term, s sub 1, we just have a 1/2. Now on the other hand though, s sub 2 is 1/2 plus 1/4. And if we add those together, we actually get 3/4. Okay. S sub 3 will be 1/2 plus 1/4 plus 1/8. And if we add those together, we will get 7/8. Now, I'm certainly not proving this, but you may believe, because there is a pattern here, and I hope that you'll accept my explanation that the pattern that you might imagine is in fact accurate. S sub n would be 1/2 plus 1/4 plus 1/8, and we would continue this until we got to 1 over 2 to the nth. And we can show it, but I don't want to go through all that work right now. The result we will get here will be 2 to the power n minus 1 for a numerator and 2 to the power n as the denominator. And so if you can verify for s sub 2 and s sub 3, that's accurate. And it's true actually for any n value. So what we're going to see when we look at this sequence of partial sums, okay, is going to look like this. The very first entry will be the first partial sum, which is 1/2. The next entry will be s sub 2, which is 3/4. The entry after that will be s sub 3, which is 7/8. The entry after that will be 15/16. The entry after that will be, let's see, I believe 31. Let's see, 1, 2, 3, 4. So it would be the fifth entry, and that will be 31 divided by 32. And this is going to continue, okay? It's going to continue. Now, the question is, and of course the nth term here is actually 2 to the n minus 1 over 2 to the n, but of course continues infinitely. And so the question is, does the limit of these s sub n's exist? And so what we would actually do, I mean, we can look at it and say, oh, it looks like those are getting closer and closer to 1. Okay, the more we add, the closer we are getting to 1. The more terms we add, the closer we are getting to 1. But here's how we would tell that. We would look at the limit of the s sub n's as n goes to infinity. And we have a formula for the nth partial sum. See, we have a formula for the nth partial sum. It's 2 to the n minus 1 over 2 to the n. So we take the limit of that as n goes to infinity. Well, this is not that difficult because we can use a little bit of algebraic magic and write that as 2 to the n over n, 2 to the n minus 1 over 2 to the n. So when we simplify this expression, we get 1 minus 1 over 2 to the n power. Now, of course, as n goes to infinity, the limit of 1 is still 1, but we would end up with and the limit of 1 over 2 to the n, as n goes to infinity, the denominator is getting unboundedly large, so we have 1 over a larger and larger unboundedly large denominator, and of course that goes to 0, so we have a limit of 1. So the conclusion is simply this, that the series that we started with, the sum from n equal 1 to infinity of 1 over 2 to the power n converges and is equal to 1. So the fact that it converges, or we have a finite limit, then we know that the series converges. And the sum is 1. That is, another way we could write this is if we take 1/2 and add to that 1/4, and add to that 1/8, and add to that 1/16, and we continue this process infinitely, then we say that the sum of that, the infinite sum is the number 1. Now, the issue that we run into with series is to come up with a formula. See, this worked out because we had a formula for the nth partial sum. And that ends up being a rough spot. That's going to be hard to come by in general. So as we get further and further into this chapter about series, then we're going to have fewer and fewer opportunities to know what the nth partial sum is. We'll make decisions about whether the series converges or diverges based on other information besides what the nth partial sum is. Well, let's next look at a couple of special situations where we can come up with the nth partial sum. So we're going to look now at a special group of series called telescoping series. And when we look at the partial sums of this, we'll see why they're called telescoping series. So let's consider, here's the series. As you see, it's the sum from k equal 1 to infinity of the difference of the fractions 1 over 3k minus 2, subtract 1 over 3k plus 1. So let's look at the first partial sum. And the first partial sum would be when k is 1. And we're only, when k is 1, we don't really have things to add up. We have only one term. And so that would be 1 over 3 times 1 minus 2, subtract 1 over 3 times 1 plus 1. And in this case, that's 1. 3 times 1, 3 minus 2 is 1. So we have 1 over 1, which is 1, minus 1 over 3 plus 1, 1 over 4. So, and I'm going to leave it that way for now. Okay, obviously we could say that's 3/4, but I want to leave it that way because next I want you to look at the second partial sum. Well, the second partial sum is going to be this. It's going to be 1 over 3 times 2, excuse me, it's the first two terms. So it's 3 times 1 minus 2, subtract 1 over 3 times 1 plus 1. So that's when k is 1. That's the first term. And then we add to that the next term, and that would be when k is 2. And so that would be 1 over 3 times 2 minus 2, subtract 1 over 3 times 2 plus 1. Now, when we do this, we already saw what this part gives us. See, this part was the 1 minus 1/4. And when we come over here and we calculate, so let's look at it that way. Okay, that's the first term of the partial sum, the second partial sum. When we calculate here, we'll have 1 over 6 minus 2, which is a 1/4, subtract 1 over 6 plus 1, which is a 1/7. And notice what's going to happen. These two terms are going to add out. So we end up with 1 minus 1/7. Okay? Now, the truth of the matter is, S sub 3 is actually going to be these first two terms. See, it's going to be these two added together from above plus 1 more when k is 3. There's plus 1 more when k is 3. And so that ends up being, let's do this, 1 over 3 times 1 minus 2, subtract 1 over 3 times 1 plus 1. That's when k is 1. Now when k is 2, we have 1 over 3 times 2 minus 2, subtract 1 over 3 times 2 plus 1. But we've got 3 terms, so now k is 3, and so we have 1 over 3 times 3 minus 2, subtract 1 over 3 times 3 plus 1. Now, we've already seen in this first case, above we got 1 minus 1/4. And in the second case, above we got 1/4 minus 1/7. And in this third term here, we actually have what? 1 over 9 minus 2, we have 1/7 minus 1 over 3 times 3 plus 1, 1/10. And so you see what's going to happen here. These pieces are going to all add out. Minus 1/4 plus 1/4 is 0. Negative 1/7 plus 1/7 is 0. And so we end up with a 1 in the beginning and a minus 1/10 at the end. Well, in general, this is what's going to happen, and maybe you'll agree with me, I hope so, for the nth term, excuse me, for the kth term, the kth partial sum. Let me start this over. So, for the kth partial sum, we're going to end up with, okay, a 1 minus, and look at this last term, okay? This was when k was 3, wasn't it? Okay, so when k is k, when we go to k, our very last term is going to be subtract what we see here. So it's going to be minus 1 over 3k plus 1. So that's what the kth partial sum looks like. Earlier I called it the nth partial sum, but I'm using k in this case. And so for our series above, the question is, what is the limit of these partial sums, in this case, as k goes to infinity? And since we know what the partial sum looks like for the kth partial sum, it is 1 minus 1 over 3k plus 1. Well, that shouldn't take us long to figure out that that's 1 minus 0, which is 1. Okay, as k goes to infinity, the second fraction that we're subtracting is going to 0. So what's our conclusion? Okay, our conclusion is then, that means the sum, the sum from k equal 1 to infinity of 1 over 3k minus 2 subtract 1 over 3k plus 1 converges to 1, because that's the limit of the kth partial sums. That's the limit of the partial sums. And so we once again have convergence. Now, this series is called a telescoping series because it collapses. You know, that makes me think of the old children's toys, children's telescopes that collapse down into a little tube and expand out. Maybe you played with those when you were a kid, but that's what it reminds me of. That's why it's called a telescoping series. Okay, now, in general, this is what a telescoping series is going to look like. Let's look on the next page. As I was saying, in general, a telescoping series is, without using the summation notation, the sigma notation, it's one when you expand it, we would have a b sub 1 minus a b sub 2 plus a b sub 2 minus a b sub 3 plus a b sub 3 minus a b sub 4 plus, and this would continue forever, okay? And so if we were looking at the nth partial sum here, then this would go until we, pardon me, until we had, in this case, a b sub n, okay, minus a b sub n plus 1. But the point of it is we're collapsing in the middle, and we're left only with b sub 1 minus b sub n plus 1. If we have a telescoping series, that's the way it will look. And so the series would converge series converges provided that the limit of s sub n as n approaches infinity which would be equal to the b sub 1 is a fixed number, okay? It's the b sub n plus 1 that's getting bigger and bigger, or changing as n goes to infinity. So it would be equal to b sub 1 minus the limit of b sub n plus 1 as n goes to infinity. And so if this is finite, then this limit there is finite, then the series converges. That is, the telescoping series converges if and only if the limit of b sub n plus 1 as n approaches infinity is equal to a finite number. problem. Pardon me. Because of the way the first example was set up, we had two fractions, one subtracted from the other. It was very clear that as we looked at some partial sums, it's very clear we saw the collapsing process going on, and so that's how we knew it was a telescoping series. But lots of times, we don't recognize something as a telescoping series. Let me show you. So here we have a series, the sum from n equal 1 to infinity of 2 over 4n squared minus 1. And this doesn't look anything like what we've been seeing, where we would have this collapsing in the middle. And so we don't recognize this as a telescoping series. But this term, let me write this down, okay? If we consider partial fraction decomposition, of this nth term, see, we have a sub n, that's what we're adding up, which is 2 over 4n squared minus 1. Well, we could write that as 2 over, I may have scrunched myself up too much here, I hope not, 2n plus 1 times 2n minus 1. And so a partial fraction decomposition, we could have it in the form as a over 2n plus 1 plus the fraction b over 2n minus 1. Okay, so we could create that scenario. Now, whoa, you might say, how would I know to do this? Well, of course, that's what being a scientist and a mathematician is about, and an engineer, is we have to gather tools, we have to remember tools, and we have no idea anything's going to work here, but this may be a way that we can work on this series when nothing else will work. So as we go through this, please just allow me to, I'm not going to do the decomposition, but you could do it on your own. And if we do this decomposition, we end up with negative 1 over 2n plus 1, okay, plus positive 1 over 2n minus 1. Now that could actually be rewritten as 1 over 2n minus 1 subtract 1 over 2n plus 1. So we could replace this fraction in the summation with this difference of fractions. And that looks like something that might be a telescoping series. So that's what we're doing over here. Let's go back to our original problem and let's consider this series, the sum from n equal 1 to infinity of 2 over 4n squared minus 1. And we've just said that that fraction is the same as 1 over 2n minus 1 subtract 1 over 2n plus 1. Now, as we consider the infinite series, say when we consider n being equal to 1, that would end up looking like what? So I'm just going to come down here. If I started adding up these terms, well, when n is 1, we would have 1 over 2 times 1 minus 1. 1 over 2 times n minus 1 would be 1 over 1, which is 1. Subtract, when n is 2, we would have 1 over 2 times 1 plus 1, or that's 1 over 3. And then we would change n to 2. And when we change n to 2, we would get 1/3 minus 1/5. And then when we change n to 3, we would get 1/5 minus 1/7. And of course, this goes on infinitely, but we can see what's going to happen is if we just go out to n terms, what we're going to end up with is a 1 in this first position. Everything else in between is going to collapse until we get, see, it's this last position that doesn't collapse, and this last position is when we have an n value, and here it was n was 3, but in general an n value, and so that will be minus 1 over 2n plus 1. So that's what the nth partial sum looks like. And so now we can say, well, what's the limit of these nth partial sums as n goes to infinity? That is, what's the limit of this 1 minus 1 over 2n plus 1? Whoops, plus 1, as n goes to infinity. And we know, of course, that limit is in fact equal to 1. Okay? That limit's 1. And so the conclusion is that our original series, which was the sum from n equal 1 to infinity of 2 over 4n squared minus 1, is equal to the number 1. Now, each time here we've had a summation of 1, okay, that the series converges. See, again, this means it converges. But and each time we've looked at these so far, we've been converging to 1. But that's not always the case. That's just coincidental here. Now, there's another type of special series that we can come up with the nth partial sum of, or we can make a decision about the convergence or divergence and what the sum would be if it converges. And we'll do that on the next page. They're called geometric series. As I just said, here we're going to talk about another special type of series called a geometric series. Let me write down an example. So we start out with 3, and then we're going to take that 3 and multiply it by 2. So plus 3 times 2. And then we're going to add to that 3 times 2, and we're going to multiply by 2 again. So that will be 3 times 2 squared. And then we're going to take that and add, and we're going to multiply that by 2 again, and so that will be 3 times 2 cubed. And then we're going to do the same thing, 3 plus 3 times 2 to the 4th, and we're going to continue this forever. This is called a geometric series. Now, this particular number right here, we generally represent with an A. And this number right here, we generally represent with an R. Okay? And so if I was writing this out in more general terms, well, let's do it this way. We could say this is the sum from n equal 0 to infinity of 3 times 2 to the nth power. Now, starting at 0 rather than 1 is a convenience, so things fit nicely. Okay, this is a convenience. See, when n is 0, we have 3 times 2 to the 0. And since 2 to the 0 is 1, we just have a 3. And then when n is 1, we have 3 times 2 to the first, or just 3 times 2. And then when n is 2, we have 3 times 2 to the second. And so you see, we have exactly the series that we see above. Now, this R, by the way, is called the common ratio. And in pre-calculus, then we study series, ratio, not ration, common ratio. The more general look to geometric series, the general look is this. Follows exactly what I've shown. It's the sum from n equals 0 or k equals 0, whatever we decide our index is, but we generally start at 0 and go to infinity, some constant a. In the above case, the constant was 3, times some constant to a power n. And so this would look like a plus a times r plus a times r squared and plus a times r cubed and forever in this pattern. Okay, that's what that series would look like. Now, let's consider the nth partial sum. Okay, let's consider the nth partial sum. What I want to do is tell you that we can get a formula for the nth partial sum. So this is going to take a bit before, but I want you to see this so that you're not just accepting what I say. Okay, so a formula for S sub n. Okay, that's what I want to come up with. And so here's what I'm going to do. If we look at S sub n, okay, S sub n means we add up the first n terms. And so this is the first, this is the second, as we look up here, this is the third. And notice the power on R is one less than the number of positions. So S sub n will look like A plus A times R plus A times R squared plus A times R cubed. And it will continue for a while until we get to, let's come over here, A times R to the power n minus 1. See, the power on R is one less than the position of the term, and we're adding up the first n terms, so the power on R is one less than that. And so right before this, we would have a power on R that is one less than n minus 1. Now, here's what I want to do right here. I want to multiply that S sub n by R itself. And so I'm going to say take R and multiply every term up here by R, okay? And so when I multiply A by R, I'll have A times R, and I'm going to offset it. You see, I'm going to put it over here. And then when I multiply A times R with R, I'll get A times R squared. And when I multiply A times R squared with R, I'll get A times R cubed. And we'll continue this, okay? Now what's going to happen is we're going to continue until, oh, I've kind of ran myself out of room. When we multiply the term that we see right here by R, we'll get A times R to the n minus 1 power. See, we'd add 1 and n minus 2, the exponents on R, to get n minus 1. And then when we multiply this last term by R, we'll get A times R to the power just n. Now what I want to do is take the S sub n that's right here and subtract the R times S sub n that's right here. And notice that when we do that, see, just look above. With the A that we have here, when we subtract, there's nothing below. It's just going to be an A. But these are going to subtract out, aren't they? All of these are going to subtract out. And everything's going to subtract out until we get to the very last term on the bottom, and we'll have minus A times R to the n power. Okay, because we're subtracting that bottom row, aren't we? That bottom sum. Now, a couple of things from here. When we look at the left side, this nth partial sum is a common factor. And so I'm going to factor it out. Okay, factor it out. And what I'll have left is 1 minus R. When I factor S sub n out on the left side, I'll have 1 minus R left. On the right side, I have a common factor of A. Okay, so I'm going to factor A out, and I'll have A times 1 minus R to the power n. Now, what I'm really trying to do is come up with the formula for S sub n. So what I'm going to do is take this left side and divide out the 1 minus R. And when I do that, on the right side, I'll have the A that I've got there, and I'll have a fraction where I have 1 minus R to the nth power in the numerator and 1 minus R in the denominator. So this is the formula for the nth partial sum, and it's based on A, the constant, and R, the common ratio. Now, what we want to know is what's the limit of S sub n as n approaches infinity. And so that would be the limit of A times the fraction 1 minus R to the n over 1 minus R as n approaches infinity. Well, here's the significant part. A is just a constant, and R is just a constant. The variable part is the N. Okay, the variable part is the N. And we saw earlier in the semester that the limit of R to the N power as N goes to infinity is equal to 0 if the absolute value of R is less than 1. And we saw that the limit of R to the N as N goes to infinity is plus or minus infinity if the absolute value of R is greater than or equal to 1. R could be negative, and that's when we would get a negative infinity. So when we look at this limit exists only in this case. That is, this limit is A times 1 minus 0 over 1 minus R, provided the absolute value of R is less than 1. If the absolute value of R is not less than 1, then we have 1 minus infinity or negative infinity, and so the limit would not exist. And if we simplify this, this is A over 1 minus R. So that actually is the formula for what the summation is. So let's look at this. Let's go to the next page and put this together. So in general, for a geometric series that we see here, the sum from n equals 0 to infinity of A times R to the n power, if the absolute value of R is greater than or equal to 1, then the geometric series diverges, which means it doesn't have a finite sum. On the other hand, okay, if the absolute value of R is less than 1, now what does that mean? That means R is a number that's less than 1 or greater than negative 1. Not equal to 1 or negative 1, is between negative 1 and 1. Then the geometric series converges. And furthermore, what's really important here, furthermore, it converges to something that we can calculate. Okay? And what is that? That is the sum from n equals 0 to infinity of A times R to the n power, R to the power n is equal to A divided by 1 minus R. That's what we just saw on the previous page, because that's the limit of the nth partial sums. So for a series of this type, one, we can tell real quickly whether it converges or diverges by looking at the R value. And once we know it converges, we have a formula for knowing what it converges to. So let's look at an example here. Okay, and this example is determine, well, let me write it out. Okay, so here's our problem. Determine if this series from n equals 0 to infinity of 3 over 2 to the n power converges or diverges. If it converges, what does it converge to? Now, this is not so uncommon. Sometimes it doesn't appear that we have a geometric series. So let me rewrite this series. The sum from n equals 0 to infinity of 3 to the power, 3 over 2 to the power n. Now the first thing to notice in this case is that we can take that nth term, that's what we're taking the sum of, and write it as 3 times 1 over 2 to the nth power. So it's looking closer to a geometric series. Now, that 1 over 2 to the nth power, see, that 1 over 2 to the nth power, we could actually massage a little bit more. we can say this is the sum from n equals 0 to infinity of 3 times, and 1 over 2 to the n is the same thing as 1/2 to the power n. So now we have a situation where we recognize that this 3 is the a value and this 1/2 is the r value. And so since the absolute value of r, which of course is the absolute value of 1/2, is in fact equal to 1/2 and less than 1, then we're a go. We have convergence. And another way to look at it is our r value is between -1 and +1. That's another way to look at that. Well, once we know that we have convergence, then the formula, remember, is a over 1 minus r. And in this case, the a is 3 and the r is 1/2. So that ends up being 3 over 1/2, and 3 over 1/2 is 6. So this sum adds to the finite number 6. This infinite sum adds to the finite number 6. Well, after these examples, so what have we seen so far? We've seen two special types of series. One was a telescoping series, the other a geometric series. And from those two special types of series, we can actually determine convergence or divergence. And not only that, we can tell what it converges to, okay, if it converges. And that won't happen often, but it does in these two cases. Now, I want to next, and I'm going to do that maybe in addition to this discussion, I want to next talk about properties of infinite series that we'll use over and over later on.